So next speaker is Kenghagho from University of Bremen, and his talk is about perception through cognitive emulation. To be honest, I have no idea what cognitive emulation is.
Thank you very much. Yeah,
I think it's something that's going on all day in my brain, yeah? But I'm happy to learn.
Yeah, thank you very much. It's a privilege really to have this talk here today. And I will start with a brief story of me. As master students, having a lot of machine learning lectures and so on. And you said, okay, this is what I will be doing. I will be teaching robots to learn and so on. Then when I started my PhD program, I was like, okay, integrate the perceptions group. So I'm like Kenghagho Kenfack from the Institute of Artificial Intelligence at the University of Bremen, supervised by Professor Michael Bates. So he already held a talk today. And so this is some things on my story, saying, okay, I will learn things on perception and so on. I will just try to say, okay, have this model, takes the data, the images, fit in the model and so on, and they will detect the environment, they will detect the object and so on, and you're done. So I learned some things. So after conducting a lot of experiments, being involved in some project, as you will see here, what I noticed is perceptions appear to be a very, very, very complex problem. So not just okay, object detections or pose estimation, and we are done, and somehow, and for many reasons. And what I learned from that is the right solutions actually require to know also the right problem. And the right problem requires you also to be at the right place. These are three problems that we identify on perceptions when you introduce those agents in very complex environment. And here, we focus at the University of Bremen on everyday activity, shopping activities, where you have a supermarket and so on. You have household activities, kitchen, cooking, and so on. And now we have also lab automations activities. Then we identify three major problems. The first problem is sensor limitations. It appears that sensor data are very limited, with respect to what we want to get from those sensor data. When you see from those images that I collected to illustrate what I mean by that, you see that in the frame one, the robot is trying to get some things from the shelf, but it should succeed that with limited view of what is in the shelf. This is the first thing. The second thing is what the colleague already illustrated, like a transparent object. So we said, okay, let's use a technology to escape, let's say, the problem. We took the technology, RGBD image camera. We said, okay, they fail at detecting or are perceiving black object because they absorb the light, or glass because they retransmit the light, and so on. And we start to say, oh, how to solve the problem. And we take those data and we fit into model. We have two consequences doing this. Those data are really high entropy data. So when you try to learn from those data, you get nothing. Because learning is basically a kind of data compression. So learning is fundamentally a compressions problem. And when you try to learn from those data with very high entropy, you get almost nothing. And what happens is you just you just try to make your system bigger and so on to increase the number of weight and so on. And what happens is you just memorize the data and so on. So you don't actually learn. That is the first thing. Or if you try to interpret such high entropy data, you get nothing because they don't have informations. Because the entropy here is basically the lack of informations. So when you see the informations in the generator that actually produce those images, and you see the amount of informations in the produced images, there's a very large difference. So you get almost nothing. So the first problem is the sensor data are very limited. We cannot just rely on sensor data to actually understand what is in the world, what is the state of the world. The second thing is the lack of anticipation. It's when you start to deal with dynamic environment. Let's see, for example, this case where you have like a stack of apple. If I ask you to grasp like one apple, you might say, okay, I will grasp this, I will grasp it. But they have like all different consequences after grasping one. So it's not just a matter of detecting like one apple, but what is the consequence after grasping this? There will be a consequence. Who is responsible of this? You say you are the perceptions. You are the one to tell about the state of the world. So you are the one to tell what will happen after that. You can see, for example, that at the frame 4, the robot trying to place some things on the table serving. It's not just a pick and place like in Amazon or where you take the carton and you just throw it. You should make sure that when you place that bottle, it doesn't fall. And it depends on a lot of things. For example, the dynamic of that bottle, the amount of liquid in that bottle, the way you release it. And you should anticipate this. You should not put it, it fall, and you say, oh, it fell, and so on. And this is very important, for example, in the mission critical, let's say, environment, like a lab environment, where you should really make sure that you don't damage like things. Will you release a bottle and damage it, regret, and buy another one and restart? Or you should really make sure that if you release it, you won't get damage. Such types of things. And it causes us to realize a lack of explanations in actual systems. Compression is, or our learning is a compressions problem, and compression is not always learning. So when we see the things that have been proved on like a deep learning system, how they can be full, a deep learning like detecting a car, you just change the pixel, it tells you that it's a bird, some things like this. And then you ask yourself, do those systems actually learn or decompress? Learning is compressing, but compressing is not always learning. Then we ask ourselves, how do women actually solve such types of problems? How do women actually overcome those problems? And it comes out that the solution actually is emulations, cognitive emulation. What is cognitive emulation? Is that we maintain a set of representation and process mentally that allow us to realize mentally the change of the world, either in the past, in the present, or in the future, to actually be able to anticipate no matter the amount of data we have, the amount of information we have. So in contrast of classical perceptions, where we try to extract information from sensor data, what we realize is perception is mostly going from the inside out. So we spend our time generating a world, imaginary world, and that we adjust with the few available sensor data that we have. So what is the content of those cognitive emulation? You should be able to mentally visualize or to mentally represent like images, what you call mind eye. You should be able to actually execute the actions and have the effect of those actions also mentally before engaging in the real world. You should be able to understand physical causality, how objects behave after interaction, or when you interact with objects, how they behave. You should be able to understand functional causality, that is how activities relate to each other. If I see the robot having some things, and I see the effect of that things on tomato, for example, when you put that on tomato, you get the tomato cut down, it actually means that that object that the robot has the disposition to cut, and by definition, it's a knife. So you can actually get some things like this from the sensor data, and so on. So this is what we have. And so there's a video here that basically shows a bit, illustrate what I've said. For example, you see you have like the sensor, you have the internal representation of the stimuli. For example, can you put a pause? Can you pause the video, please? Back. Can you move forward? Yes, so here, if I ask you what is here, what do you see here, for example? Yeah. No, can you pause the system after the face, please? yes, after the face, there's a face there. Oh, it doesn't move forward? Okay, or that just play? Okay, so if I ask you, what do you see there? So if you just, rely on sensor data, you will not be able to recover this, or it's really ambiguous. And this is what happened in our everyday life. This is also what happened at the airport. When you arrive there, there's a loudspeaker, really, really noisy, whoa, 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 and then people start to react. Do they react because they actually understood what was said, or because they have an expectation of what should be said? Some things. They react because they have an expectation of what should be said. It is 3 o'clock, I am at the gate, some things like this. It is 3 o'clock, I am at the gate. When the loudspeakers start to say something, then it means it is like a boarding time and so on. So I start to move. Cool. So how do we actually, so our problem here is actually to implement such cognitive emulations capability on a robot to be able to overcome the problem mentioned above. And what we do is we actually propose a system, naive physics for robot perceptions recently. And what it does is we have, at the beginning, what it does is it actually model the world state as a partially observable hidden Markov process that evolve actually within a specific context which is defined by a lot of things and which evolve like through the physics that objects and agents in the world undergo. As you can see here, what happened is that at the beginning we have in a given context to generate like emulation, and it is based on the context. So the context is made up of the ontology of the world, which catch a lot of things like causality and functionalities. And then we have what we call also the context. It's a description of what is going on actually in the world. And research also shows that humans actually use a narrative as a cue to actually infer a lot of what is not given from the few available evidence. This is what detectives, for example, use. With a few available evidences, they will build a narrative, and from that narrative, they will recover a lot of other, invisible kinds of evidences. So we have these evidences. So from we have this narrative. So from that one, we formalize them into like a graph, a scene graph. So this scene graph is like a joint graph. It represents the scene, what should be actually in the scene, and so on, with the activities, or the ongoing activities. And what we do is that we hallucinate actually those activities, either based on what we imagine or the actions we imagine, or the actions of other agents, and we see how the world will change. And we adjust our imaginations based on what we get from the real world. I will just quickly show us a video because it's simple, and we can transfer it to different kinds of domain. This is like the mathematical formulations of the problem, and I will basically illustrate a bit how it works here. So for state estimation and awareness, for example, in TraceBot, how we use the system, this is, okay, you are here. Can you play the video, please? It's like you're running out of time. So we say, for example, we describe a situation. The robot is like performing something, and from that description, we turn the text into hallucination of, let's say, scene. So we will do a lot of reasoning, inferring like the activities, the potential actions, and so on. What objects can be or can play a role in such actions, and so on. And from that, we will imagine what the scene could look like, or will look like, and so on. Yeah, so you imagine how the scene will look like, and these are your imaginations. You don't just generate one imagination. It is probabilistic because you're not sure about if what you imagine is really what is in the world. So you have like many emulations somehow that I will illustrate. Yeah, so it goes a bit. So according to the descriptions that we gave, this is an hallucination that actually corresponds to this. And once we have done this, the next step will be to correct our hallucinations based on what we actually observe in the real world. Yes. Cool. So this is, for example, for kitchen activity, but we can also give you for medical lab activities. So here you can see that the robot maintains really a probabilistic state of what the world is, of the world, kinds of. So these are the different kinds of emulations, what we obtain. This is like for sterility test activity, kinds of. It's almost the same thing. And finally, we also show that we can use such a system to perform functional verifications in TraceBot. So this is the last video. We want to grasp. The question is, what is the preconditions to grasp successfully? Should you try and fail, or you should actually make sure that, okay, you got like a successful strategy before engaging in the real world. So you have many emulations of how to actually grasp it, and at the end you select the one that actually succeeds, and you perform it in the real world.